before I start. So I'm a computer scientist, and if you think this is maybe not quite what you signed up for, then you can thank these two people, because essentially what I work on is something called proof engineering. So these are the technologies that make it easier to develop and maintain verified systems. So what I mean by verified systems here, these are systems or programs that are proven correct in these special tools called proof assistants. So proof assistants are these tools where someone who we'll call a proof engineer, they can write a program in this proof assistant, then specify what it means for that program to be correct, and then write some kind of proof that the program actually meets the specification, that it does what they said it does. And then the proof assistant will check this proof using just a few simple logical axioms. So all of these proof assistants are based on different logics, and the proof checker will just use the axioms of the logic to make sure that this proof is correct. Then it will let the proof engineer know, that their program actually behaves that way. So, these things have come a really long way since they first came out. So, especially when it comes to the process of actually writing this proof. When these things first came out, this used to be so difficult that even experts would mostly only prove correct really simple programs. But things have changed a lot since then. So, it's gotten much easier. So people have proven correct really complicated programs. One of my favorite examples, which actually comes out of Australia, there's this operating system called Cell4. And this is, they run inside of an autonomous helicopter at one point. And because of this, they were able to, so they showed that this operating system was secure, which made it resilient to hijacking by a team of professional hackers. So cool stuff. And there's a lot of work on this. So I think if you want a good overview of this field, if you're just interested, my colleagues and I wrote a survey paper about this, all of proof engineering. And it's, it's 120 pages, not including citations. So there's a lot of stuff here. But, when we were writing this, I realized most of the work here focused on how to develop these systems to begin with, how to, write a program and then prove that program is correct, and then just, your proof is done. But unfortunately, that's not really the way programs work. You have to maintain them. These things are going to change and change and change. And as they change, you have to keep changing your proofs. So, there hasn't been that much work on how to maintain these verified systems as these programs change. So this is the focus of my work that I'll talk about. So what I do, is I build tools that are aware of the fact that, proofs are constantly changing here. And this might sound a little bit weird, I think, if you're used to thinking of proofs as sort of static entities that don't change. But I really think it's not that weird. So, let's forget for a second that we're in this world of formal proof with the proof assistant. And I heard something really popular to do during quarantine was invent calculus. So let's briefly invent calculus. People told me that Newton invented calculus over quarantine. This is not quite true. Actually, this guy Gregory, he proved correct a narrow version of this fundamental theorem of calculus. It's not quite the one we know today. And then he had a really smart student, Barrow, who was like, I can generalize this, and then he updated this proof. And then at some point Newton came along, and I was like, and he was like, I can update your calculus now. And sometime around the same time, Leibniz did the same thing. Newton was really mad at him. The point is, even in this world of mathematics, where people talk about this, as if we say one proof. We don't talk about, all four proofs of calculus. Even in this world of mathematics, these proofs are moving. They're changing. I just think in the world of math, I would say math moves like a tree. So we don't always see it moving. On the other hand, proof engineering, I would say it's like creating calculus on steroids. Like every day, your manager comes up to you and he's like, okay, I need a new calculus by tomorrow. So these things move really quickly, and we can always see them moving. This has been such a problem that back in 1977, some very smart people basically said that verifying programs is useless and we shouldn't bother doing it. So, they said, even if we can find, what they called sufficiently fanatical researcher willing to actually do this, good luck, maintaining these verified programs when they change. And then they said, there's no reason to believe that verifying a modified program should be any easier than verifying the original the first time around. And so my quest has sort of been, proving these really smart people wrong. I think there should be often reason to believe that that should be easier. In particular, if we view proofs as things that change over time, then what we can do is, build tools that automatically transform proofs to account for these changes. So, if you make a change in some kind of specification, in the theorem you want to prove, find a way to automatically, or with a little bit of help from the user, take the original proof, tweak it, and then spit out a proof of the new thing that you want. So that's what I work on. And I'll talk about that today. But before I get there, I want to talk just a little bit about proof assistance, just to give you some background here, because a lot of you have, I'm assuming, have probably never really used one of these tools before. And in this section, there will be some background. So feel free to ask questions if you get a little bit lost, because I think it's important. So I would say proof assistants sort of take Curry-Howard to its natural conclusion. They give you a programming environment, in which you can write these proofs. And I originally presented this as proofs about programs. You can also use these proof assistants to prove things about mathematics. You can use these for any kind of purpose. But the proof assistant that I like to focus my work on is this proof assistant called Coq. Now, like I said, these proof assistants are based on logical systems. So the logical system that's at the core of Coq is called the Calculus of Inductive Constructions, or CIC omega. I will break that down. So this is itself based on a logic called the Calculus of Constructions, which has been around since the 1980s. And as it sounds like, this is a constructive logic, and mostly has things that are pretty standard. Has some kind of implication, quantification, mode exponents, and then some notion of equality, which is important for computation. I'd say the only really interesting thing about this logic, and one of the things that makes it so powerful, is that this quantification, you can actually quantify over proofs and refer to them inside of your theorem statements, and then prove things about how your proofs relate to each other. So for example, you could state and prove in the calculus of constructions that all proofs of for some natural number n, all proofs of n equal n are equal to each other, and they're all equal to reflexivity. So this is a little bit wild, but it's really fun. It makes it powerful. The inference rules for this, I would say the best summary that I found, the most accessible one, was on Wikipedia. And again, there are only 5 axioms here. And I'll go through these briefly because they're still in sort of type theory notation. So this one, you don't have to worry about too much. It will get a little bit weird when we build on this logic, but basically just says we have some notion of propositions that live in some universe. And this just says we can, prove propositions, which is good. So down here we have implication, and implication proves universal quantification. And again, this is cool already because you can quantify over proofs and refer to them. Now, this is just mode exponents. It just corresponds to application by Curry-Howard. And this is our notion of equality, which is useful for computation. So that's just the calculus of construction. Then on top of that, we build in an infinite universe hierarchy. This is the omega part. That's quite a mouthful. But really, this is just avoiding annoying paradoxes because we can quantify over these proofs. So this is where this rule gets a little bit weird. Instead of propositions living in one universe, we have an infinite hierarchy of universes. And this is an infinite predicative hierarchy of universes. So every time you quantify over something in universe 0, you get something in universe 1. And when you quantify over something in universe 1, you get something in universe 2. And this goes on, forever. And this is what lets you get around these paradoxes. This gets a little bit weirder, and you don't really have to know about this, but inside of Calc, they still have one universe that doesn't behave like this, where you quantify over it and you stay there, just in case you want to do set theory the normal way. So that's the universe hierarchy. And then the last piece of this is really my favorite. There are these things called inductive types. And what they let you do is sort of extend your logic or embed entire logic, as you're using this. So with inductive types, you can define anything that you do structural induction over, essentially. And adding these to the logic really just involves two axioms. One thing that lets you construct these inductive types, and then another that lets you, do induction over them. Because we're type theorists, we give these induction principles weird names, so we call them eliminators. But I'll give you a couple examples in case you haven't seen these. So a really simple inductive type, if we're using this tool, we can define the inductive type true. And because anything proves true, we can always construct true. So it has one constructor that we can always call, just a base case. The induction principle we get for this is pretty much useless. But if we look at false, we have an empty inductive type, something that you can never inhabit, never construct. But the induction principle we get, thankfully, is that false implies anything. So that's great. We can define the natural numbers. We can say 0 is a natural number. And if we have a natural number, we can take the successor of that and also get a natural number. And then the induction principle that we get here is, the induction principle for natural numbers that we're probably used to. But, we can also do things that are way more powerful than this. This is any kind of structural induction. So you can embed entire logics and relations inside of this and then reason about them. So here's an example from a book called Software Foundation. It's just a variant of the simply typed lambda calculus. So there are types and terms, and there's a little bit of extra things that they added here for educational purposes. And then you can define the typing relation for the simply typed lambda calculus. And then you could prove things about this typing relation. So this is really powerful. This is why people use these a lot for verifying things about languages. So it's a lot of fun. And all of this comes together to form this system called Calc. Now, Calc also has a couple of extra things for the sake of engineering. And in particular, this last step of writing this proof would be miserable for most normal people if they had to just write the pure logical object directly and just have the computer check it. So instead, they use this thing called proof automation. But this is a bit of a misnomer because it's not really full automation. It's not that we just throw the theorem at the proof assistant and it will discover a proof for us. This is really an interactive kind of proof automation. So what will happen here is the proof assistant is going to help us construct this raw logical object that it can check. So when we call the proof assistant, we use these things called tactics when we're writing our proofs. So these are basically high-level strategies that look kind of like what you might see in an informal human proof. So you might say something like, just do induction. And then, the proof assistant will update your goals and communicate that back for you. So it might say solve the base case. And then, you might give it another strategy like, well, the base case is obvious. And then it will ask you, okay, then solve the inductive case. And this process of tactics and feedback will continue and continue, all the while you build up something called a proof script, which again looks a little bit like a human proof, not quite, because they're a little bit weird. It's a little harder to read, but it's a little bit informal. And but the proof assistant itself is going to discover a proof. And the proof that the proof assistant finds when you write this QED and you're done is going to be a raw logical object. And that raw logical object, is going to be something in this calculus of inductive constructions that it can actually check for you using just the axioms of the logic. So the core of the system does not have to understand so-called fuzzy concepts like obvious, but the human can still use those, which is the benefit there. So the tools that I build that transform these proofs, they're transforming these raw logical objects, but the experience of using them is going to be the experience of using this proof automation. I'm building sort of strategies for transforming these logical objects. So now I'll talk about, what that actually looks like a little bit. So again, I think just like the idea of proof changing might be a little weird, I think the idea of transforming a proof might also seem a little bit weird if you haven't thought about it before. But I think this is another place where it is surprisingly natural if you break it down. So I want you to think for a second about the world of informal human-written mathematical proofs or something like this. If you've ever looked at one of those, you've almost certainly seen the word similar or similarly. It shows up everywhere. Now, similarly, so I'll show you just one example. I wrote a proof both informally and then in the proof assistant in COP that just said that if this propositional degeneracy holds, so if every proposition is either true or false, then I can show propositional extensionality. That if P implies Q and Q implies P, then P and Q are equal to each other. And I just use similarly here. So I just want to show you what it would look like, to try to check this informal human proof. So, I start by just choosing some propositions, P and Q, assuming they imply each other. And then by my hypothesis, I have, that P is either true or false, and Q is either true or false. So then, I split into cases based on these. So when P and Q are true, I get that P equals Q, of course. Now, here I'm just going to use similarly. I'm going to say the false case is similar. Otherwise, I'm going to say, if P is true and Q is false, then I get, true implies false, false implies true. But because I can derive false, I can derive anything, and so I get my conclusion. And actually, the case where Q is true and P is false is similar. So I can get propositional extensionality. So this is one case where I use similar. But I want you to stop and think for a moment. Say I threw this proof at you, and I wanted you, the human, to check this. Figure out that this is correct. I want you to think about what you would do, because I know what I would do here. First, to check the true case, I'm just going to substitute in true for P and Q. And the thing that I get here is that true is equal to true, so that's great. But when I see this similarly, it's almost like I've installed this kind of proof automation, this strategy in my head. And I know because I had true equals true. When I say similarly false, I'm just going to substitute in false for true and check the same thing. So here we have a transformation. It's just that we're expecting the human to run this transformation. And this other case actually works similarly, I would say. It's a little bit more complicated, but essentially, you're still just substituting some true and false terms. You also have to do a little bit of swapping. But again, it's this sort of transformation that you run. So I think even sort of fuzzy concepts, or so-called fuzzy concepts, like similarly, in this world of informal human proofs, These are often things that we can mechanize. We can automate, we can teach a computer to do in the world of formal objects. It's just that we need to think about these proof objects and, modify them here for this similarly, because this is actually introspecting on the content of the proof. So, this is what I do. When I first saw this, and I think maybe this is my background, I thought this looks a lot like a program transformation. So in the world of programming languages, which is where all of my work is, a program transformation is just a program that takes a program as input, modifies it, and produces another program. And these are so common. There are hundreds of papers on this every year in programming languages. So every compiler ever, refactoring tools that people use when they are writing code to reorganize it, obfuscation tools and deobfuscation tools to try to, tweak some codes that you can hide its content or understand hidden content. These sorts of things are all program transformations. So, I like to take this, across the Curry Howard bridge here, I would say, and instead of a program transformation, I think what we have here is a proof transformation. And proof transformations, they do show up once in a while in the world of proof engineering, but instead of there being, hundreds of papers every year, they show up like once every 10 or 15 years. So I think this is a major loss because this can be used for lots and lots of things, to automatically fix broken proofs when something changes, to reuse proofs from someone else's development, kind of extract the core insight and use it inside of your proof, to optimize proofs, have a proof that's inefficient, that's going through all of this extra logic and sort of trim it down into something more efficient, to factor a proof into a sequence of proofs about lemmas that it passes through, to generalize proofs so that you can derive a more general fact from them, and to implement human-like proof strategies. Like this similarly sort of combines reuse with a human-like proof strategy. It's reusing a proof within the proof. So, all of the work that I do, I think, can really be thought of as automating some kind of similarity. So just now I want to take this sort of informal human proof that I wrote, so you can think about how we can automate this. And I want to look at the proof terms that this would actually produce if I were to write this in a proof assistant. So I actually translated this like informal human proof into Coq as a tactic script. And then I ran, I ran Coq and I looked at the output, this raw logical term. And the thing that I got maybe looks a little bit scary, but it's actually not that scary. This is, again, just a raw logical formula. So for example, here we have for ind, which is the induction principle for disjunction. And this is just splitting it into cases, one where P is true and one where P is false. Using this, our hypothesis, which I named PD, that says, for every P is true or P is false, and then applying it to P. So we split it up into cases. And you can actually see the sort of similarly inside of the proof terms. So in the case where P and Q are both true, it shows up like this. And then the bottom half, you have where P is false and Q is false. And actually, all the other details of these cases are exactly the same. So if you just do the substitution of false for true, then you end up with this other case. And then in this other part of the proof where I had this other similarly, the change is a little bit more complicated. But again, you still just have some substitution, some swapping, and everything else, just shows up pretty much identically. So this is something we can automate. We can build tools that take in, say, this half of the proof, and then we'll, spit out and do this transformation, modify this proof object to spit out something that looks like this. So again, there are lots and lots of things that we can use this for, and I'm not going to talk about all of them today, but I am going to focus on two things. So one of them is on automatically fixing proofs when something changes, and then the other is on reusing proofs, extracting the core insight from another proof or something like that. And actually, these two things are sort of the same problem. So reusing a proof, to derive a new proof. This is really implementing something like, similarly to this other proof, essentially. On the other hand, our repair is saying that we want something that's similar to our old proof. We had some old proof, we changed something, and now we want something similar that accounts for the change in our theorem or something like this. Really, I would say that repair is just reuse over time. But there's one caveat there, which is that if you're just trying to reuse a proof, if you wanted to, you could refer to the old one as much as you wanted, or to the other one as much as you wanted. You could say, because I have this other proof, I'm just going to use this result, and then, by that, I have that my result holds via something else. When it comes to repair, we're working in a world where the old proof doesn't exist anymore. We kind of want to throw out the old thing. We don't want to refer to it, which is why a transformation is really natural. So these tools that I build for maintaining these systems implement this sort of similarly over time. Now, the name of the suite of tools that I built for this is called Pumpkin Patch, and I'll just give you some comic relief. So my advisor is really into acronyms, and this is the acronym behind our tool suite, Pumpkin Patch, and it's quite a lot. But essentially it implements this kind of similarly, all of the tools inside of this. So there are a couple different parts to Pumpkin Patch in some different papers, and the key insight from our first paper here, the first Pumpkin Patch paper in 2018, was that people sometimes, when you think of a program, a specification changing and needing to change the proof, sometimes you might think of it as you just have to change a single proof. You're living in a world where there's just one program, one specification, one proof. Our reality looks a little bit more like this. You have a lot of dependencies. So you change some kind of specification, you're depending on this in a lot of different places, and you're going to have to tweak all of those proofs if something changes. And that's going to be a lot of work. So our insight here was that rather than have the human go in and fix all of these proofs one by one, what we can do instead is take the insight from just one of these changes. Let them make an example change for us. And then, we find sort of the key change that this describes, describing the change in the specification itself, and we use this to fix all the other proofs. So we're generalizing a single example patched proof into what I call a reusable proof patch. So actually, in this case, the transformation that we're doing is over the example change. So it's a little bit different than some of the other things that I'll show you later. But here we really have similarly to this example change that I've made. So this part works by a proof transformation, but there's one more part to this pumpkin patch, which is this kind of different thing, because in order to generalize an example change to one of these proofs, we have to be able to figure out what changed between the old and new versions of a particular proof. So we have to be able to look at, the user's giving us an old proof and a new proof, and we're trying to sort of extract the key insight from that. And that doesn't look at these crazy looking, human-ish written proofs. It's going to look at these raw proof objects. And these actually look kind of, they're super structured. They look like trees. As of course, anything you can do structural induction over is going to look at some point like a tree. And so, for example, here is sort of the representation of a proof about the natural numbers. So any proof about the natural numbers, using induction over the natural numbers. in one case, you're going to show in the dotted line that P of 0 holds. And in the other case, you'll say, if n is a natural number and P of n holds for that n, then we can show P of the successor of n. So any inductive proof over the net is going to look like this. Now, if we have two of these, we're going to get these sort of two trees that are superstructured. And if we want to figure out, what it is that changed between them, we can actually look at the differences in these dotted lines. We can search, do a sort of semantic differencing between these trees. And then we can try to, I would say, sometimes I say we're looking inside of a relation between two proofs for a proof of a relation. So, we're searching for this key insight that we can generalize. And then we'll transform that because that will be specific to a particular proof. But it won't quite be something that describes the change more generally, something that we can use in all of these other proofs that have also broken from this change. So we'll take this and we'll transform it using 4 different proof transformations. So I won't go into a lot of detail about how these work, but they have pretty self-descriptive names. So specialization just means that we're going to take a proof of something that's a little bit too general and specialize it. Abstraction says, we have something that's too specialized, so we'd like to abstract or generalize it. Inversion says, we want a proof of P implies Q, but we got a proof of Q implies P. And this is sort of like similarly in the opposite direction. Sometimes, due to some inherent symmetry, you can swap, you can actually tweak a proof of P implies Q to derive a proof of Q implies P, and we can automate this. And then the last of these is factoring, which is taking a proof that passes through a whole bunch of proofs of lemmas along the way and breaking it into pieces, which is natural. For example, you'll need this if you want to invert something sometimes, because if you're trying to invert G of F as a proof, then you want that you need to invert. Sometimes we'll need to invert F and invert G and stick them back together. So G of F inverse is F inverse of G inverse. So those are the 4 transformations in this original work. And this is really good for what I like to call changes in content. So changes where your old and new proofs are going to have the same structure. So they'll have the same shape. These trees will not have any additional nodes in them, or any additional arrows, any new hypotheses. But it's not very good for changes in structure, where you're going to be adding and removing things here. So, if you're inducting over something different. So that's been the focus of a lot of my more recent work. Some of it is work in progress. So I'll give you a couple examples of some of these changes in structure, and then I'll talk about how we actually do this, because this gets pretty interesting. I introduced earlier this inductive type for the natural numbers. You can go from the type of natural numbers to the type of lists very easily. So essentially, you have a list of elements T. So a list takes a type T, and then we say that just like 0 is a natural number, now nil, the empty list, constructs a list T. And then the cons case, which looks a lot like the successor case, says, if we have a list of T, and you give us a new element of type T, then we can, construct another list of type T. We can cons that element onto the list. And the induction principle that we get for this, is exactly the induction principle for the natural numbers, except that it has this additional element in the cons case. So that's one change we can make to the structure. Now, we can even take this a step further. And this is fun because this uses the fact that we can quantify over and refer to proofs. We can build a special kind of list where, in order to construct this list, you need to prove its length is a certain number, so it will carry around its length. This actually combines a list with the natural numbers. So it will look like this. We have a list of length n. The empty list, nil, has length 0. And if you give me a list and you prove to me that it has length n, then I can give you back a list of length successor of n and a proof, that it actually has that length. And the induction principle we get for this, it looks exactly like the induction principle for lists, except that it's carrying around these lengths everywhere. So then every time you use this, you have to write these proofs everywhere. But it's a really cool change. Now, again, because this is so complicated, you're carrying these proofs everywhere with you. Even though these are super powerful, they're extremely hard for people to use. So here are some quotes from experts in the area on these vectors that I just showed you. This is what we call them, vectors. So someone said that they are not suitable for extended use, and someone else said almost no one should be using them for anything. So even though this is a change that is not really that complicated, it turns out to be pretty infeasible when you're mechanizing these proofs by hand, to actually adapt your proofs to this change. So the key insight that we had in some of our later work was that we could actually automate, almost all of this for certain kinds of changes in structure. So things like if you give me a proof about lists and proofs about their length, then I can give you back proofs about vectors. And these proofs about these vectors, will not refer to the proofs about lists at all. So it will induct directly over this new thing, over this vector. And furthermore, unlike before, where I needed you to give me an example change, for this change, actually all I need to do is peek in at the difference between these data types, this list and this vector. And from that, I can change all of your other proofs for you. So you really don't have to do any additional work once you prove something about lists and their lengths. So instead of transforming an example patch proof into a reusable proof patch, here what I'm doing is, actually I think a little more intuitive. Just transform every single old proof that you give me over lists and their lengths into some new proof over these vectors, and just do that directly. And so this is really this similarly to this old proof. So this uses a proof transformation. It still has a differencing step here. So all of my work on reuse and repair combines this proof transformation with some kind of differencing to take away steps that a user might have to do manually. So this differencing here, though, is not going to look at the change in your example patched proof. It's going to look just at the difference between these theorems or types. So it's going to look at the data type that you've changed. So it will just take in a list and a vector. And from looking at these, it's just a procedure that operates over the induction principles of both of these. It can discover the length function. And then from that, it can prove two particular equivalences. It can show that a list is equivalent to a vector of length n for some n. So there exists n, such that there's a vector of length n. List and vector are not themselves equivalent, but these two things are equivalent. Or we could also show that a vector of length n for a particular n is equivalent to a list and a proof about its length. So that means, anytime we have proofs about one of these, we can derive proofs about the others. So this is how we get proofs about vectors from proofs about lists and proofs about their lengths. And the proof transformation will then just transform the proof across this equivalence. I guess one thing to note here is that these equivalences in this logic, this is not our core notion of equality. equality and equivalence in this world are different. Equivalence just says there exist two functions, let's call them f and g, that are mutual inverses. So f of g is always going to give you back the original element, or g of f will give you back the original element. But equality is a much simpler concept that just involves things like alpha, beta, gosh, I don't even, there are like 4 Greek letters there. I lose track of them. But so, we can't just let the computer do this right now in this logic. But what we can do is transform our proofs. And this is sort of the cool thing that we implement here. So we're not transforming an example change anymore. We're transforming the old proof directly. And we do this using this proof transformation so that there are sort of, so one thing you could do, for example, if you've discovered that 2 things are equivalent to each other, and if you have a particular axiom or some useful machinery, you might be able to say, well, I had this thing that held over this old type, so, I'm going to take my thing and I'm going to convert it along this equivalence, and then I'm going to sort of call my old proof, and then I'm going to convert it back. If you did that, you get proof terms that become really unwieldy. They'll become very large, going back and forth across all of these equivalences, and they'll be pretty slow to compute, which matters, when people are really using these things. So by doing a transformation, we're able to just change the induction principle instead of converting back and forth. So we're no longer inducting over lists, we're inducting over vectors. This gives us small and fast proof terms, and it also means that we can handle this case of repair when the old thing does not exist anymore. So, all of these tools inside of Pumpkin Patch implement these kind of different notions similarly. And we've used this with some good results to replay some changes in some famous software. And we have a partner who's actually using this in industry right now. So it's been fun. And I think has really given me, at least, and I think others at this point, reason to believe, that verifying a modified program, is in many cases easier than verifying the original. But there's a big sometimes there. So in particular, if we try to think about every single change that we could ever make to a proof, the space of all of those changes is massive. In particular, this would give us every single proof of our old theorem and every single way to prove our new theorem. So very big, infinite, so we can't really talk about handling all possible changes. This is obviously undecidable. As a computer scientist, the first thing I did here is I thought about, well, okay, what are the changes that humans are actually making, and can I classify them? So I did a user study. The main reason I'm briefly talking about the user study is because we built a tool with another acronym, which will also provide some comic relief because it's an acronym within an acronym, which I'm very proud of. But essentially, this let us listen into the development processes of proof engineers for an entire month as they went about proof development and look at the changes that they were making. So we could figure out the changes that matter to people. And I was hoping that these would correspond naturally in some way to transformations that matter, proof transformations that we can classify and implement. It actually was not that straightforward of a translation. It helped, but I really ultimately found that this was somewhat of an art. Picking these transformations, even once you've classified the kinds of changes you can make, is not totally straightforward. So a lot of my recent work has been, I would say on correct art. So this is still going to be an art necessarily. There will be some creativity involved. But I would like to be able to give you a framework where you would like to define a transformation over proofs and sort of plug it in and have my tool execute this with some other information and know that certain guarantees hold. And there are sort of minimal things that I can ask you to show me such that that is true. And so this is some work in progress. I'll talk about this a little bit. It's going to be fuzzier than everything else because it's still going on. So I guess the sort of key insight here is, earlier I showed you this equivalence with lists and vectors. Well, I think really any change that you make to a data type when you're changing your proofs, I think you can view any of these in some light as an equivalence. But it's not going to be just an equivalence between your old thing and your new thing. I think it's really what you're looking at. Sometimes you're adding information or removing information. So this is an equivalence with some extra information. Or more formally, this will be, sorry, give an example. With our lists and our vectors, the extra information that we're adding here is that we're passing around these lengths. We're proving this length, all the time as we construct these vectors. So that's the extra information. And, we get this equivalence. Here we have this extra, n. We have this vector of length n for some n. Or, we could say that if you want a proof over vectors, I'm going to need more than a proof over lists. I'm also going to need a proof of other lengths. Really, more formally, this extra information here, what we have is an equivalence between existentials or sigma types. So we can sort of squint and view it this way. And then what we can do is transform proofs to preserve this equivalence. And there's actually a really nice way to state what it means for this to be correct, even in this complicated world where you can quantify over proofs. And it involves something called univalence. This is an axiom. It actually does not hold in the logic that I'm working in, but it basically says that we can treat equivalence and equality the same way. But this is what we can use to state what it means for a transformation across an equivalence to be correct. But again, it's not an axiom in our logic. And, in fact, it's not provable in our logic. But we are lucky because it is consistent with our logic. So, what we can do, I would say, is we sort of use univalence meta-theoretically. So I would say this is like univalence inside of the metalogic. The metalogic that I would use, to prove a transformation like it's correct, I would say, we use univalence to state this correctness property and to prove it. But because we're doing a proof transformation, we don't actually need univalence at any point inside of the logic itself. So I think that's kind of fun. And again, because we're doing a proof transformation, we get some of the same benefits that I was talking about earlier, these small and fast terms, and we can handle repair. Now, this is a work in progress, but I've defined a transformation like this. This is actually missing one rule that I really want to add that I just figured out yesterday that deals with equality a little bit. So this is a bit of a narrow version, but essentially, I define a transformation that will transform proofs over some type A into proofs over some type B when A and B are equivalent. But as always, there's a catch, which is that these three things here that I've circled, this lift a limb, so dep a limb here, dep conster, and ID eta, these are not primitives in our logic at all. So this is the thing that you sort of have to instantiate to your equivalence between A and B. And then you're lucky because everything else will just kind of go along automatically. But this is not, always totally straightforward to define. I would say that this is the art. So, you really have to think about a way to do this that is useful to people and that is interesting. So, here, just for some motivation for why, you can just use any transformation. For this list and vector, we could transform, proofs about lists to proofs about vectors and, of length n for some n, or we can transform, this one that I showed you earlier, proofs about lists and their lengths. But we could also do a lot of really ridiculous things, like we could require, additional proofs of true. We could do this infinitely many times. So there are infinitely many, bad ideas here. But, so you'll have to be a little bit clever, I think, in some cases, to think about a transformation here, an instantiation of these three things that really makes sense. And it's actually going to be these four things when I add the additional rule of equality. But what's good is that once you have defined these things, we can actually say something about how they are related to each other. So there's a correctness statement for what it means for these things to be related to each other, such that when it holds, then the rest of the transformation will work fine. So that's exciting. And this is thanks, the correctness statement for the entire transformation is going to use univalence. But the statement about these three things, well, one of them uses univalence. But yeah, it's a work in progress. I'm excited to share it when it's done. Now, like all of my other work, there's a combination of both a proof transformation and a search procedure. So I don't want this part here of defining these things. I don't want this to have to be something that you do for every single A and B. That sounds really painful. So instead what I do is I think about sort of classes of changes from A to B. So things like going from something like a list to something like a vector, where you're adding this this proof of this. So this length here was something that we could determine by a function just over the old thing. There's an entire class of changes you can define this way. You can track the size of a tree. You can track the minimum element in a tree if you're able to have, if you have a function where you can actually compute the minimum. So you can even add invariance this way. So for an entire class of changes that work this way, I've already written, just a little bit of code that will look at your old one and your old type and your new type, and it will spit out the right instantiation for these so that we can just run this transformation. And we've done that for 4 or 5 things. Now, major asterisks, as always, of course, we can't always search for arbitrary A and B without some help from you, for these things. And furthermore, we can't even automatically transform any arbitrary term that you give us, any arbitrary proof term. There have to be some restrictions here. And this is fundamentally because we're working on an undecided, or on an interesting problem. And we know by Rice's theorem that everything interesting ever is undecidable. So, that's one sort of annoying thing there. I would say another annoying thing is that the transformations that I'm defining are over these raw logical objects, but the human is not going to want to get back one of these when they've written this nice, this human-like proof, this more informal proof using these tactics. Because if they want to modify it later, they want to continue making changes, then they're going to want back something that looks like what they had before. So what I do here is I have an undergrad by the name of Ronzer who has written something called a reverse compiler. It's actually going to take in a raw logical object in Cup, and it's going to produce from that these sort of high-level strategies, one of these proof scripts. And that's what we'll give back to the user in the end. So that's a lot of fun. I've talked about 2 of these things that I use these proof transformations for. Again, there is a lot more that I can talk about at some point. So feel free to ask if you're interested. Before I, wrap up, I want to finish, and this is maybe a little bit weird, but I want to finish by actually asking you guys some questions, although you can ask me questions after that too. And this is just because I really basically never get a chance to talk to logicians who don't call themselves type theorists. So here are some things that I've wondered, where I think maybe some of you guys might have some insight. So I spoke briefly earlier about the fact that I can use this to optimize proofs as well. So what I can do is I would say optimization is reuse within a proof. So say that I have a proof that does induction too many times, and there's a proof that does induction fewer times. Actually, what I found is that if you look inside of the proof and you run some kind of, I can actually run some kind of tool that will discover inside of it the proof that has fewer levels of induction. So it will pass through the more optimal proof all the way, and then I can take that out, transform it, and get something more optimal in that sense. Or I might have something that goes through a whole bunch of extra lemmas along the way that it doesn't need to go through. One of my favorites is I saw a proof, or I just wanted to see what would happen if I tried to prove that 0 equals 0 using a decision procedure called omega, just a famous decision procedure. And the proof that it gave me back was like, assume 0 is not equal to 0. Then, and it went on and on and on. It was essentially like that. But then buried deep inside, was the use of reflexivity that I needed. So it's cool. I can, sort of take it out. But I've been wondering, I give you sort of a couple notions of optimality here. Obviously, there's not going to be one canonical optimal proof of any theorem. But I wonder if there are, some notions of optimality here that I could use. Maybe optimality for a particular induction principle, or something like this. So I would love to hear, if you all have any background here, where you have anything I can point to, it'd be interesting. Now, okay, second question. I sort of took this axiom of univalence, I sort of bumped it up into our Metalogic, implemented this proof transformation, and then what this transformation is really doing is sort of realizing univalence on an ad hoc basis. So instantiating it, to particular proofs, even though it's not pulled in inside our logic. So I want to know a couple things there. I want to know, what other axioms I could do this with. What would be some fun axioms to try? Where else has this sort of thing been done? It would be really cool. And then, I'm also wondering to what extent. Is this something that I can always do? To me, it feels sort of like a finite approximation of an infinite fact. Univalence, the statement itself is, saying for any equivalence, I can treat this like equality. But here what I'm saying is, well, you've given me a particular equivalence, then I can, find a way to treat it like equality. So I just want to know, is there, something deeper going on there? It seems interesting to me. And then finally, this is actually, it sounds like a weird question, I think, but just believe me when I say this is one of the most practical things. Like, I know people who, like, I could probably find millions of dollars of funding about this question. So one thing I really wonder, everything that I do is about reusing proofs within the same logic, transforming proofs within a single logic. But in the world of proof assistance, we have many, many different proof assistants, all with like slightly different logic. Almost all of them that are popular these days are some kind of higher order logic, but a very different one. So one thing I wanted to know, if I want to build a tool that transforms proofs from one of these proof assistants in a different logic to another one, I would really like a way to state what it means for that transformation to be correct and prove it. But to do that, I have to sort of relate these different logics. And I want to know how I can do this, if one of them isn't a metalogic of the other. Is there sort of like a common metalogic? Is this a thing that people have done in this world? This is one thing I'd really like to know. I'd like to thank all of my collaborators, and I'm just going to leave up some of my questions for you, but you guys can also ask me any questions that you have. Thank you.